Howdy, everybody. I hope you're having a good time wherever, whenever you are. I truly do hope things are going well for you. Today, I just want to do a little interlude. I still want to get to some stuff. Life's busy, but I try and do some daily problems. I don't do it every day, but I happened to do one on Leetcode the other day, a few days ago, and I just thought I'd share that with you. So, spoilers, really quick. You'll get the answer to day, was it 20? So I guess it's technically yesterday's, but I do it the nighttime, in the nighttime, so I do it the night before. Anyway, it's number 1980. That's what we're talking about today. I'll include the link down in the description. And just as an aside, Leetcode is kind of a fun place to try and solve little puzzles, especially if you only have, like, I don't know, 20, 30 minutes, maybe an hour. I mean, it may take longer if you're very new to solving coding problems, but in general, you could probably figure it out in 30 minutes. At least do a brute force solution that you might not be able to. Maybe you don't solve all of the test cases, but you solve some of them, and then you can come back the next day and figure it out. Anyway, they have daily puzzles that they do, and you can see I don't do really well. I've only solved 4 in the last 2 weeks, and even fewer this month. But, when I have 30 minutes in the evening, maybe I'll try and do one. And this one, the reason I want to share it was it kind of caught me off guard as to, like, the optimal solution to it, or at least a solution that I hadn't thought of before. And so I just wanted to take a moment to share it with you. So let's just talk about the problem really quick, and then we'll go over my original solution, and then I'll show you, like, this new solution that was in the editorial. I think the editorial is like Leetcode's solution and possible ways to solve it. But sometimes you have to be a premium member to do it. I don't think I'm currently a premium member. Anyway, feel free to become a premium member. I think these are really helpful if you're into programming and you want to just kind of start picking up and keeping your chops, every day. Okay, let's talk about it. Find unique binary string. So it says, given an array of strings, nums, containing n unique binary strings, each of length n, return a binary string of length n that does not appear in nums. If there are multiple answers, you may return any of them. So here's the example they give. This is kind of hard to grok sometimes because it can feel very terse, especially if you're coming from, like, Advent to code or whatever. So think about it, is you're going to be given an array of strings that are binary strings. There's going to be n of them, and each of them are length n. So you can think about it, if each character, there's going to be n characters in each line, and then there's going to be, like, n rows, right? So you're going to get a square is maybe the way to think about it. And your job is to find one that isn't in there. So they give you an example. If there's 0, 1, and 1, 0, you could return 1, 1 because 1, 1 is not in this array. And then they give you another example, 0, 0, 0, 1. You could do 1, 1 again because it's not in this list, right? The same thing here. This time, though, it's a 3, 1. So you see there's 3 elements, and then there's 3 characters per element. So there's these 3, and this one is not in it. There's several that aren't in this one, right? And one thing to pay attention to is it always gives you constraints, right? It always says, like, here's some things that will help you understand the bounds of the problem. And I think it's important to actually read and understand these because they can help you infer what's going on. So in this case, it's saying n is equal to nums.length. So if you say, what is the length of this? It's 2. Then you know there's going to be 2 rows, right? Because that's the length. But you also know each of these are only going to be a length of 2, right? And that can help you in the sense that, like, you have to produce a number of length n, so yours has to be 2 as well. You can't just do random gobbledygook. It has to be 1s and 0s, right? Yeah, right here. Nums I is either 0 or 1. And then it says n is between 1 and 16. So this is something where I said, oh, well, if it's between 1 and 16, the list isn't actually that large, right? So you'd really have to be given a lot of test cases for you to like expend a lot of effort to try and solve it. Does that make sense? If n could be like 1,000,000, then you might say, oh, I probably need to do some optimizations. But because n is 16, less than or equal to 16, you know there's just not going to be a lot of cases. And so probably even the brute force solution is going to work, right? Or maybe not brute force. I mean, I suppose brute force is okay here. It's probably more like a naive solution. Anyway, says all strings of num are unique, and each of the lengths of each of the numbers is n. So these are all like the constraints, right? And again, these should help you infer in your mind what optimizations do I need to do. And in my case, I kind of thought, you know what, I'm not sure I need to do any optimizations. There's probably not much I actually need to do here to optimize it, mostly just because, again, it's very small. So the solution I came up with was, let's just turn these into actual numbers, right? It's never going to be more, there's never going to be more than 16 of them. So if you think about it, like even if there's 2, so there's 2 numbers here, but there's a potential for 4 numbers from this set, right? 0, 1, 2, and 3 from this set, but only 2 of them are there. So you just have to pick one that's not in there. So my thinking is I'm just going to turn these into numbers, keep them in a hash set, and then just check, right? I'm going to start at 0 and see if 0's in there. And if it's not in there, then I know I've found my solution. And if you think about it, that again, because the constraint is small, this should always work, right? And it especially works as n gets larger, right? Imagine 16-digit numbers, binary numbers. Now you have, you know, you have the potential for the 16 numbers to be very large, but you'll never have to check more than 17 times, because even if they were the first 16 numbers, like 0 through 15, and you just start checking at 0, you'd find the next one at 16, right? And so 16 would be your answer. Well, I hope that makes sense. But the idea, maybe I can draw it really quick. The idea is you create the numbers. So let's go with this example right here. Let's do this example right here because it'll at least let us go through it. So we have 0, 0, and 0, 1. Okay. And so I'm just going to turn these into actual decimals numbers. So this is 0 and this is 1. And now I'm just going to do a for loop. So I'm going to go for 0 to n. I know it won't. I don't think I did n. We'll have to go see. It's not actually n. I probably just go forever. But then I can just ask the question. I put these in a set, right? So I create a set. And I say for I in that, I say if set dot contains, sorry for the chicken scratch, I think I actually do if not set dot contains. I can just return I, right? I may have to turn this into a string, but this is the general idea. So I'm just going to loop through all the numbers and find them. And again, the reason why this is, I think, performant is you're only getting, this loop will never occur more than n times. And you'll only ever do this thing n times. Like this is the worst case scenario is 2n, which when you're doing like on stuff is just generally O of n, right? So I'm never going to do it more than n times, and so it's just never going to be a large number, and you probably can't get faster. In fact, most cases it's going to be faster, right? Like you can see in this case, there's no 0. So after I've like converted these to decimals, 0 is the winner. This one too, there's no 0 in here, so 0 is the winner, and so it happens very fast, right? So let's look at that code and see how I do it and see if I remembered how I did it. here's my solution in Rust. Basically, I just get n because I think I use it in other places. Oh yeah, I do right here. Yeah. I convert all of the so I'm given this vec of strings, and I convert it to a vec of ints. I think it's like it probably turns it to I32 or something like that. Oh no, usize. I say usize right here, right? So I iterate over them, convert them all to usize, and then I collect them all out, and then I sort them. Why do I sort them? You probably actually don't have to sort them because it's this, again, the list is so small. But I basically just say until I find my answer, I'm going to loop through all the numbers from 0 to n, and I'm going to do a binary search on this thing. Again, because it's sorted, I can do a binary search. And so if I don't find it, so it's an error. Oh, that's funny. I didn't put it in a hash set. I probably could have, and it might have been faster. It's interesting that I had mentioned doing it in a set before, but I didn't actually do it here. This was 2 days ago. I wonder if this is actually faster. You get the same answers, right? I presume you get the same answer. But if you ever fail and don't find it, then I break, I know I'm done, and I can just return that number as a binary string. And so that's what this is right here. I just return it as a binary string. And I mean, that's it, right? You're never going to, again, you're never going to have to search more than n times. And I think that's why this is n right here, right? Is because even if it's like a very large, this is like, even if it's like 20 or 16 or whatever, you'll never have to search more than, you'll never have to ask for the first more than 16 because they can only produce 16 numbers, right? Or I guess the first 17, right? So in this case, I'm doing n plus 1 because I have the equal. But you'll never have to ask more than the first 17 numbers if they're in there because they'll never be more than 16, if that makes sense. And so that's why this works and why this is really fast. So I did it and I solved the problem. And I actually don't even remember. We can go look. I think I got it relatively fast. Yeah, here's the initial submission. The memory is low and it's like the runtime is 0 milliseconds. It basically was all like, you're super fast. And I imagine most people get 0 milliseconds on this, again, because there's only 16 of them. Okay, so now you're probably asking yourself, why are you even talking about this if it's so easy to solve? Well, it is easy to solve until you like read the editorial, which is what I did, right? Is I read the editorial. I'm like, okay, how did other people solve this? Or what are some other solutions? Did I do it okay? Things like that, right? And in the editorial, it says, another way to solve this is with Cantor's diagonal argument. And so I just want to go there and talk a little bit about Cantor's diagonal argument and why this works. And as I'm talking about it, you'll probably understand why this helps with the problem if you haven't already been yelling at it to me as I've been describing this, right? I won't go into the details of like why he has this argument. It largely revolves around infinite sets. And basically what he showed was that like some infinite sets are different than other infinite sets. There's not like a one-to-one correspondence between the infinite set of natural numbers and other sets. And he proved it with this diagonal argument. And what the diagonal argument says is, if you give me a list of numbers, he uses binary in his case. If you give me a list of numbers, I can give you a new number. I can always give you a new number by just iterating over every single one of your numbers and changing the nth value in that number so that it's different from that nth item, right? So at the 0th item, I swap the 0th one. So if I have a 0 here, I set it to 1. And on S2, if I change the second one to it's a 1, so I set it to a 0. And I do that so on and so forth. They call it diagonal because it produces this diagonal right here. It's like if I do that so on and so forth, I will always have a unique number that you have not put in your set. So why is that the case? Well, it's definitely not equal to S1 because you've swapped this value in S1, so it can't be S1. It also can't be S2 because you swapped this value in S2 as well, right? So essentially what you've done is every single value in this number is different than a value in each of the other items going this way. And it kind of ensures that the numbers are completely different from each other. So let's, like, can I move? I can't remember how to move. Oh, is it space? Let's just try an example of this so it makes sense. And we'll use this right here. We'll use this one right here. 111011001. Okay. 111. All right, forgot them. 11 and 1. Okay, so these are the numbers I have. And now how do I do this? So for the first row, I just say, okay, what is this value? And I'm going to do the opposite of that one, 0. Now I do it right here. What is the value here? I'm going to do the opposite, 0. Now what is the value here? So like this is the 0th position. I'm going to just like do the diagonals, right? So 0 0 1 1 and then 2 2, it's 1, so I'm going to put a 0. So you can see clearly here this number doesn't exist in this set, right? This is a new number that you've been given. And he did some cool stuff again to kind of prove that there's a difference between these countable sets, or sorry, infinite sets. And again, I didn't take enough math that I remember exactly how he did that, so I don't want to go too far into the weeds with that. But if you've been following along, you may say to yourself, "Oh, I know why. Now I know how to use his argument, his theorem to like solve this problem, right? I don't even have to ask which 16 there are. I just have to do a different digit in each place, and now I'll get a unique number for sure." And once you work through that, you actually realize that they gave you the correct answer in here, right? Oh, I may have done this the wrong way. Did I do this the wrong way? I did this the right way. Why did they give 101? I don't know why they gave 101. But these ones for sure are it, right? It's like, because if you like put these together and you say, oh, 0 and 0 and 0 and 0, they both give you 11, right? If you had like, I don't know how you'd get that, but it's really cool in my mind that Cantor's argument solves this. And that's what I thought was cool about this that I wanted to share about you is somehow if you know about Cantor's diagonal argument, this problem becomes somewhat trivial, right? Now you know, oh, I can just swap all the values on the diagonal, and now I get a new number, and it's just as fast. I don't have to do any guesswork. I don't have to do any checking, right? If you remember, my original solution was find all the numbers, sort them, and then go through the list until I find one that's not there. Again, we could optimize this, and maybe we will in a second. We could optimize this and make it faster, even more so. But the point is, we don't even have to do that, right? We can use Cantor's diagonal argument to solve this. Okay, so what does that look like in code? I'll get there. It's right here. And if you like the functional style, it literally is just this, right? So we iterate over all the numbers, we enumerate them because we want to find the ith element of each string for that point in time. So that's what I do here, right? I say, give me the string as bytes and return the ith one. And then I ask myself, is it a 0? I make it a 1. Otherwise, I make it a 0. This is just a swap, right? So this is get me the ith element or the ith character. And then this one is swap its value and collect those up as a string. That's all there is to it. Much cleaner, much simpler. Okay. So this compared to this, and even this, right? I could clean it up. In fact, let's do that really quick. How would we do that? We might say, let's just collect it into a hash set of usize. Then we don't even have to sort it. And then if we do not nums.contains I, we can just go like that. Do we use that anywhere except for here? I guess it's a different nums.lang. Oh, we do use it twice. So primate this. So this will surely still work. Yeah, it still works. But think about it. It's not strictly ON. It's very small, right? This is N, right? Because I think these hash functions are O1, right? So this is N, and this is N2, so it's like 2N. It's kind of double N, right? And in like big O notation, like 2 times N is essentially the same as N, so you kind of fudge the numbers unless you really want to be strict about performance. Sometimes 2N does matter, I guess, but usually don't. In this case, though, it quite literally is N, right? Just get the ith element, find the thing, and collect it. We're literally doing it once, as opposed to here we have to do it twice. So it's definitely faster. Okay, hopefully that kind of piqued your interest as like how cool Leetcode can be. Is like, oh, that's so cool. That you can like, you read this editorial and it, by the way, it kind of bugs on Firefox. I don't know why. It takes a minute to boot up. Anyway, you read this, you try and solve a problem, and maybe you get it solved. It's not perfect, but you do get it solved. And then eventually you say to yourself, oh, that's really cool. I'm going to see how it was solved. And the editorial has an even cooler way, right? And it gets you excited about programming. This is the thing. This is the reason why I love programming, is like finding these cool ways to solve problems. And I do this at work too, right? Is you spend time finding the right algorithm, finding the right data structure to do the things to solve the problem. And it kind of like sparks this light in you. Like I remember after seeing the Cantor solution and solving it, like feeling so like, whoa, that's so cool. And I hope you feel that way about this too. And maybe you're new to it, and so everything feels new. And I know when I was new at it, sometimes it felt more stressful because I didn't know the answer. And I guess what I'll say too is it's okay if you don't know the answer, or you try and solve it, and maybe you can get a couple of the test cases to work, but not all of them. And then you go look at the editorial for the actual solution. That's totally fine. It's okay if you don't know the solution. It's okay not to know the solution, and it's okay to go look at the editorial or to go look at how someone else solved it. But you can still get that same excitement of, oh, that's a really cool solution. I would never have thought of Cantor's argument. I think the first time the last time I should say, I read about Cantor's diagonal argument was in some video from like some math science YouTube video or whatever. It was very new to me, and I was like, oh, that's really cool. Probably never use that. And so it like flew out of my head until I came back here and I'm like, oh, that's right. What a cool solution. So this is all to say, just do some daily programming. Maybe you don't like Leetcode. That's fine. Go find some way that you can do some programming and spend some time thinking about it, right? It's okay to think about it. If you haven't spent time thinking about it, even when you're coding on a day-to-day basis, I understand if there's deadlines, right? Sometimes you got to get the deadlines done, but make sure you have time to go back and refactor and rethink and optimize and make it more readable, make it more understandable, use algorithms that you hadn't thought of at the time, right? And that's, I think, what will help bring joy and help you improve in your programming, right? Is if you're always looking for ways to improve. And maybe that's watching these videos so you get new ideas, or you go try and solve problems. Maybe that's going and solving these problems yourself, or it's also collaboration, right? Collaboration is important because other people have other knowledge and they might be able to share things that you don't know, and you in turn can share things that they might not know, right? So just be on the lookout for learning and growing. That was the whole point of this. Is it's okay to learn and grow and to not know all the answers, but hopefully you will get excited when you find new and cool ways to solve problems. And in this case, the new and cool way was Cantor's diagonal algorithm. Again, I don't think my original solution or even this solution here is bad. I think it's totally solvable. But how much cooler is it to solve it with this way, right? So you can see my unit tests are all the same, right? I do unit testing on these, but I'll include the solutions so you can look at them in the description of the video. But hopefully, again, I've piqued your interest of, hey, I should be programming every day, even if it's not my job. And if it is my job, I should be taking time throughout that day to, review my code, to make improvements, to Google or ask AI or something. Is there a better way to do this? And what is that better way? So hopefully you'll do that. Hopefully you had a lot of fun. If you've been solving Leetcode problems and you found one that you liked, or any other website that you think would be a great video, just send it to me in the comments, and maybe we'll include it in an upcoming video. So there you go. Have an amazing time whenever you are, and we'll talk to you later.